Hi, welcome back to Unit 4, revision for electrical and electronic principles for years 12 and 13. And we finished the last video looking at Ohm's law, and we looked at power and energy. And we're back to looking at Ohm's law to some extent, but we're just going to focus now on resistors. And you'll see both these questions are asking you about values of resistors, but also, again, Ohm's law, the voltage, the current, and the resistance within a circuit. So, let's have a look at this question. So we've got here a digital multimeter used to measure the value of resistance between points X and Y in the resistor network shown in figure 1b. So we're going to be looking at the resistance across this. I know it says 3.3 kilo ohms. Okay, so you sort of think, well, why we look it? But this question isn't going to actually ask you that. It's a practical question, and you will get these where it will test your practical knowledge of setting up, how to do some soldering, how to set up a multimeter, how it should be set up. Explain how to connect the probes to measure the value of resistance between points X and Y. And this is about understanding that, for example, on the multimeter, if you look very closely, if I can actually bring up, it's not a brilliant image, but you can see here it says COM for common, and that common is basically where the black lead would go to the lower part of the circuit. If we assume it's positive to negative, so the black lead would go to the Y and the red lead would go to the X. Okay, and it also asks you about setting the multimeter. So we know the multimeter has, being a multimeter, it can measure volts, resistance and current, and it can also, sometimes it has an AC, and it can test transistors. So you need to be familiar with your practice of applying a multimeter. So go online, have a look, or come and see me and make sure that we've covered that information for you. So a little ping there was a battery warning. What I'm more interested in is this part of the question here. Calculate the value of resistance that will be displayed on the multimeter. But I'm actually more interested in the total resistance in this particular circuit, because actually that raises some very interesting formula or theoretical work with regards to resistors. Resistors in series and resistors in parallel, which I'd really like to cover. It's covered briefly in year 11, so go back and watch the year 11 videos for resistors, but we're going to cover that in this question here. So, if we have a quick look at this circuit, what I want to do is, and again, this is me talking to you about redrawing things, because actually redrawing things will help you understand, because at the moment these two look like they're in parallel, and it's a sort of, it's not a deliberate trick, but it is the examiner finding out whether you actually understand the diagram, whether you can see through sort of simple arrangement to actually see the truth of what's actually in front of you. So at this point here the circuit splits. So if I redraw that with a split, I start to see what's going on. On the top line I've got a resistor followed by another resistor, and then it comes back to a junction. So I draw that. Junction. And if I follow this point and come this way, I come to a resistor and back to that junction point there. So in fact, actually, going positive to negative, I've got these two are in series, one after each other, and then that combination of total is in parallel with this one. So resistor total for series would be R1 plus R2. We just add them up. So we follow that. We had 1 kilo ohm and 3.3 kilo ohms. So our total there would be 4.3. And here we've got 1.5 kilo ohms. And like I say, if you've referred back to the video for year 11, you'll hopefully have resistor total for parallel is 1 divided by 1 over R1 plus 1 over R2 plus if you've got a series of 3 in parallel and so on. So that's looking like 1 divided by, well, we've now got that total there. So we've got 1 divided by 4.3 kilo ohms plus 1 divided by 1.5 kilo ohms. I'm going to leave these as kilo and work my answer through from there. So I like to do things in stages. So I'm just going to do 1 divided by 4.3 there equals 0.2 plus 1 divided by 1.5 equals 0.6. It's going to recur, so 0.67. So we're going to end up with a 1 divided by 0.87. One divided by 0.87 equals 1.149. Remember, it's in kilo ohms resistance. So that total of these in parallel, so those in series and those two in parallel, would give me a total of 1.149 kilo ohms of resistance, the resistor total for the parallel. I've calculated the series and then added it into the, and you will, that's a complicated sort of question, but you will get that sort of level of working through just for a few marks. You need to be familiar with your series and parallel. So looking at this second paper, again we've got a resistor network. Okay, now we've got voltage here, we've got current, and we've got resistance. So we've got all of Ohm's law to play with here. And we're also going to, I'm going to introduce and remind you about the theory of Kirchoff, Kirchoff's first and second laws with regards to Kirchoff's current law and Kirchoff's voltage law. So, Kirchoff's current law. Kirchoff basically said was that if you've got a current coming into a node, now a node is this sort of thing. Any point, that's not a node, that's just a corner, and it effectively becomes a straight line. A node is a point where there are more than two exits. And Kirchoff's very common sense said that if you've got 2 amps coming, if you've got current coming in, then you should have, if there's a node, the total value there, so that's adding plus 2 in, this is taking 1.5 amps out, then here must be another negative 0.5 amps. The value at the node should be 0. So I made that observation, and it's quite a useful observation, because obviously if you're doing measurements around a circuit and these things don't add up, then there's clearly a problem. So it's worth remembering the application of Kirchoff's current law. At a node, the values should equal 0. So 2 amps coming in, there has to be 2 amps going out. Yeah. So if we've got 1.5 amps going here, we can deduce that one's 0.5 amps, or vice versa. He also had Kirchoff's voltage law, which again wasn't massively complicated. Just going to put 24 volts on there. And then we'll just put 2 resistors in. So we've got sort of 24 volts at the top rail, and it should be 0 volts at the bottom rail. So the potential should drop to 0 as you go round. So if we've got plus 24 volts here, then it has to get used up going around the circuit. So we're going to show that. Okay. So both are 24 volts, and we've got 2 amps thrown on the circuit, and we've got 8 ohms of resistance here and 4 ohms here. So the voltage, and this, you might recognise this, it's very similar to a potential divider, potential being voltage being divided in a ratio over 2 different resistors, and we can actually show how that voltage is divided up. Well, if you know, it's used up here, it's used up here, so the result is 0. So we start 24 at the top. So what voltage is being used by the 8 ohms? Well, our old favourite, Ohm's law, V over I equals R. So the voltage here should be the current times the resistance. Well, we know the current's 2 amps times a resistance of 8 ohms. So we've got 16 volts here. Now you might automatically be able to just, well, if we've got 16 volts from 24, then this should be 8. Well, let's just check that calculation. So we've got 2 amps I times the resistance of 4 equals 8 volts. So we've got 8 volts here. So we've shown that Kirchoff's voltage law is true. That if you start up on the top rail with 24 volts and you work through the components, the voltage will be shared out as a ratio across the resistance. So we've got 8 ohms here, at 2 amps, so we've used 16 volts across that resistor. So the larger resistor uses up more voltage, and the smaller resistor uses up less voltage. But all of the voltage is used up. So Kirchoff's voltage law, the potential from 24 volts on top rail down to 0. So it should be 0 volts when you complete the circuit. I hope they're useful, and again, it's going to partly apply to, or the use of Ohm's law or Kirchoff's laws can be used to work out these resistor networks. And what I want you to do is have a think about this. It says calculate the value that will be displayed on the voltmeter. So we've got 24 volts here, we've got a current, we've got 1 amp here, 2 amps here, we've got 24 volts and 16 ohms, so you could work out what the current is on there. You've got the voltage, you've got the resistance, use Ohm's law. You can also work out the value of this resistor. You've got 6 ohms there. You've worked out, you've seen Kirchoff's voltage and Kirchoff's current law, and you can use Ohm's law again to work out what the value of that resistor would be, and then you would be able to work out what voltage would be shown across that resistor. It's a bit like doing this calculation here. So I'm going to leave that with you. I'd like to try and work it out, and we'll look at the answer in the next video.